Hey everyone, we're going to talk about Atwood machine problems today, and before we get started, there's just a couple of pointers or pieces of information that I think would be helpful as we start to look at these problems. So the first idea is, what is an Atwood machine? So the picture that you're looking at is your traditional Atwood machine, and this is an apparatus that's used to study constant acceleration motion. You can tell from the picture here that you've got a pulley, which you'll see right over here, and then usually two masses. Now there can be other Atwood machines where we have, maybe a second mass hanging on the left side here for a total of three. And then there's modified Atwood machines that we'll take a look at later on. But here's your traditional Atwood machine where you have two masses. We can call them M with a subscript 1 and M with a subscript 2 to tell them apart. A light string, and then an ideal pulley. And we'll discuss what are the characteristics that make a pulley ideal. Okay, so when we think about that string or that rope, the tension in the rope can be considered to be the same at all points if the following assumptions are made. And I want to talk about these assumptions because I think when you first read the language, for example, massless, you might say, wait, nothing is massless. Why is this problem telling me that the pulley is massless? So we need to assume that the rope or the string is so light that it won't contribute to the mass of the system. So that the mass of the string is light enough that it's not going to add additional inertia to the system, to resist a change in motion. Similarly with the pulley, so we're making an assumption that that pulley itself is massless and that we wouldn't be adding that into the total mass of the system. And the third assumption is that there's no friction between the pulley and the rope, because if there was, then this tension force that we find that's competing with maybe the weight force on one box is not exactly what's happening. If there were a friction force, then the acceleration would actually be less. Okay, so some tips for problem solving. Just remember when you're dealing with ropes or strings or any of these tension forces that ropes only pull, they don't push. So if you're uncertain about the direction that a rope is exerting a force on a hanging block or something, just think about the idea that ropes only pull objects, they don't push. Ideal pulleys are frictionless and massless. So if you see language that the pulley in the following problem is ideal, all that means is that that pulley can be considered to be frictionless and can be considered to be massless. Remember that if you have objects that are connected, like in an Atwood machine, then the magnitude of the acceleration of both of those masses is the same because the boxes are connected. And the last thing to remember is, remember that the first thing you want to do is determine the acceleration of each of the objects in your problem. And then what I like to do once I do that is I consider whichever direction the objects accelerate in to be my positive direction, and I really take a moment to assign that sign convention for myself. Okay, so now that we have the tips here for problem solving and we have a good idea of where we're going, let's take a look at our first Atwood problem. Okay, so here we have a traditional Atwood problem. We have two hanging masses, M1 and M2, and let's say we're given information that M1 is greater than M2. Well, if that's the case, then this is my heavier block. I know that the acceleration of this block will be downward and that M2 will experience an acceleration upward. Okay, now that I have that figured out, I like to think about which sign conventions I'm going to use. So I know that M2 will move this way and M1 this way. So I drew in this arrow here because this arrow is going to represent what I want my positive y direction to be. And something that is important to note here is that if that is how I'm going to assign the directions, then what ends up happening is if I consider just the M2 system, then and my y coordinates for this system, then upward is positive and downward is negative. But when I take a look at what's happening on the left side of the pulley here, if I think about the sign convention, I'm ending up with the downward direction in the y to be my negative and the upward direction to be my positive. Okay, first thing I like to do when I have a problem like this is I like to analyze the system of both boxes. Every time I do this, I make a note to myself about what the mass of the system equals. So in this case, the mass of this system is the sum of both masses. So this is going to be M1 and M2. The next thing I do is I redraw my Atwood machine. So the only purpose of a pulley here is it changes the direction that a force is exerted. So if I think about this Atwood machine straightened out, and I think about the axes that we're using here, so I have a y-axis I'm going to draw in here. Okay, and along my y-axis here, M1 is going to be pulled this way. This is my positive direction according to what I have done over here, and this is my negative direction over here. I want to start to think about what are the forces responsible for what's happening. So just grabbing another color here on my pen because I'm going to draw a free body diagram. So I'm going to draw some force vectors right on the sketch. M2, if I consider this whole thing my system, M2, sorry about that, pen's not working, is being pulled down by the gravitational force, so in other words, M2G. And M1 is being pulled in the opposite direction. If M1 has a greater mass than M2, this vector is longer here, and this is M1G. So at this point, I'm able to write a math statement for what the F net is. So my F net in this case is going to be M1G plus, and I can see that this M2G is in the negative direction, so this is going to be negative M2G. Now, instead of net force here, I can sub in mass times acceleration. The mass of this system, remember, is M1 plus M2. Okay, and then when times acceleration equals M1G plus, oh, well, that's going to be plus a negative M2G, which is really like minus. Okay, so I better make this minus M2G. And my goal here is to find the acceleration, or find an expression for the acceleration. So what I'm going to do here to get acceleration by itself is I'd like to divide both sides by this M1 plus M2. And I get A is equal to, I can factor out this G on the top, M1 minus M2 all over M1 plus M2. So I was able to use the system of both blocks to find the acceleration. And I don't know if I would have been able to do that with just one single block. Because if I take a look at either of the single blocks and I want to do a force diagram for them, like for example, let me consider M2 here. So let me do a new force diagram where just my system is only mass 2. So the mass of my system is just M2. My force diagram here is going to be M2G I know that the acceleration vector is up. I can tell from over here that my acceleration vector was up. So therefore my net force vector is also up. So this means that the force upward, in this case that's the tension force, is going to be greater than M2G. But I'm not really sure what it is. Okay. The acceleration of the entire system is the acceleration of either individual block, right? So what I can do here is I can do the same thing I did for the system of both boxes. I can write a math statement, sigma F, and actually sum my forces. So in this case, this is going to be tension plus negative M2G. Okay, the next thing I can do is when I think about this F net, I have mass, which is M2, times acceleration equals tension minus M2G. Okay. I'm looking for my tension force here, and I'm going to add M2G to both sides then. And now I've got tension is equal to M2A plus M2G. And I know a lot of you probably want me to clean that up, so I'll go ahead and do that. I can factor out the M2, so I'll do that. And it's just A plus G equals tension. So now I have an expression for tension as well. One thing to notice is that in order to find the acceleration, I needed to analyze the system of both. But to find the tension, I actually needed to use one of my individual blocks as the system. Okay, the next video in the series is a video that includes some quantitative problem solving. So if you'd like some more help with Atwood problems, feel free to check that one out. And I hope you all have a great day.